They are not the same. Multinomial is like an extension of categorical. So see, categorical, the difference is that multinomial is like several, independent trials of some categorical variable.
But aren't like multinomial several Bernoulli?
True, yeah, but you can look at it both ways, right? So you have a k-sided die and dice, and then you throw it certain number of times, right? So each side has some probability. So if you throw it just once, that is categorical. So one of the k numbers will come up, and the probability will be say pk. That will be categorical. Now if you repeat this experiment, then your binomial, that character comes in.
Okay, okay, okay. So it's like Bernoulli and
Yeah. So you could say it's an extension of binomial in some sense, where it's not just each trial is not just a Bernoulli, but each trial is a categorical.
okay.
Okay, so what we'll do is the rough plan is, we'll go through logistic regression, then what is it? Naive Bayes, Kanan, Softmax regression, and SVM in this order. And I'll just go over important parts of all these algorithms, and you can stop me if there are any questions, right? So that is what we'll be doing. So the screen is visible, right?
Yes.
Okay. See, my mic is kind of slightly away from me, so there are two things that I want you to tell me. If you hear some noise, or if my audio is not proper, let me know. I will be typing on a keyboard quite often, so if that sound is disturbing, let me know. I'll switch to a more uh, a better keyboard so that it doesn't create this noise. Okay, so the first thing that I want to talk about is this distinction between discriminative and generative models, right? So if you recall discriminative models, we said this is what we said, right? So it tries to learn p of y given x, right? So that is what uh, discriminative models try to do, whereas generative models, they try to learn the joint probability distribution p of x comma y. So this may be a bit vague, right? I mean, this may not be clear. At least to me, it is not very clear. So here's one example that you can relate to. This I borrow from Professor Arun Rajkumar. As you know, he did the optimization part, right, for MLF. So this is an example that I borrow from him. So it's a very good example. I would like you all to keep this in mind whenever you think about discriminative and generative models. So this is the setting, right? So assume that you are given two audio clips, right? Two audio clips. Uh, One of them is in Bengali and the other one is in Tamil. Okay, so these are like two audio clips, and you give it to two persons, right? So person one is say an American, right? So he doesn't know any of the Indian languages, right? So you give it to him, and you tell him to distinguish between these two audio clips, right? So he doesn't know Bengali, he doesn't know Tamil, he has never heard anything, anyone speak Bengali or Tamil before, but you give this person two audio clips. Now chances are that by just listening to the different sounds, right? Maybe not, let's say not two audio clips, let's say you have uh, two, say 200 audio clips, right? 100 of them are in Bengali, 100 of them are in Tamil, a typical data set. Okay, so chances are that as this person listens to a lot of Bengali clips and a lot of Tamil clips, he will kind of learn to discriminate between the two, right? Without actually knowing either Bengali or Tamil. So do you all agree to this proposition? Do you think this is possible? Any thoughts?
Yes, it's quite possible.
It's quite possible, right? So I just listen to the sounds. There are some sounds which are distinct, which are like peculiar to the Bengali language. There are some which are peculiar to the Tamil language. Like for example, the character Ra is there only in Tamil, right? And in Bengali, likewise, I don't know Bengali, but there might be something which are distinctive about Bengali, and this American need not know the two languages, but somehow he can if you give him an audio clip, right, after listening to 200 audio clips, if you give him a 201st audio clip, he'll probably be able to distinguish between the two, right? He'll say that this, he may not give tags to them properly, but he'll say that this is this category, this is that category, right? So this is an example of a discriminative model, right? So now I'll come to the second example. Person one is an Indian, okay? So let's say an Indian who speaks Telugu, okay? So he doesn't speak Bengali, or he doesn't speak Tamil, or rather, I should come the other way, right? He's an Indian who knows both Bengali and Tamil. I put it that is the correct way to. So an Indian who knows both Bengali and Tamil, right? Now, if you think about this person, if you give him an audio clip, right? You give him the same 200 audio clips. It's actually not needed, but let's say you just for the sake of argument, you give him those audio clips, and the 201st audio clip, just like the American, you give him that. Now obviously he'll be able to distinguish between the two, and I say that the discrimination or the distinguishing act happens by the way of a generative model. Okay, so do you get the analogy of what is happening here? Why I am calling the first process discriminative and why I am calling the second process generative? Anyone, any ideas? Okay, so
Karthik first.
yeah,
Karthik, first one is clear, but second one, why do you say generative? Because
okay, right,
it's so very logical that the person knows both the language, and
Yeah.
you're feeding him with both the audio
Right.
clips of.
Yeah. So okay, so maybe I'll put it this way. See, the Indian doesn't know Bengali and Tamil to begin with, but let's say he, through the process of listening to conversations, he learns the language, right? He learns the language. So what is happening here is this person too has a model of p of x comma y, right? It's not just the sounds that he learns to distinguish, right? He learns the language itself, right? I have a model of what an audio clip in Bengali actually looks, I mean, what it means actually, right? I understand the language, and as a consequence, the classification task becomes kind of very simple, right? So I get to understand the source of the data in some sense, and that's why I call this generative, right? So the moment I know how to model p of x comma y, p of y given x is kind of very simple, right? So whereas in the case of person one, he doesn't really need to know to understand any of the words that are spoken, right? All that he needs to know is that these sounds kind of are pertinent to Bengali, these sounds are pertinent to Tamil, and therefore he can separate the two, right? That is p of y given x. You don't really need to understand the languages. All that you need to know is how to differentiate between these two when they are given a test sample. Okay.
Just a quick question.
Yeah.
But even in generative model, we are really finding p of y given x, but through naive Bayes. In this case, we are using Bayes, that therefore we are going for a joint probability. So are we really learning p x y, or are we still trying to learn only p y given x, but using Bayes?
Yeah, so good point. So see, we are actually trying to learn p of x comma y, right? We are trying to model p of x comma y, right? P of y given x then becomes simply an application of Bayes rule, right? See, the Bayes rule, we use it only in the last step during inference, right? So the whole learning is actually associated with this part. This is just like see that's why this analogy is very helpful, right? If I know the language, identifying a new clip is trivial in some sense, right? The bulk of the effort goes into understanding the language or understanding the data, which is what p of x comma y is doing. Okay, so just think about it for a while. I think at least I felt this to be a very useful example. Okay, anyway, so coming back, we will now begin with logistic regression. So what do we have here? I'll just go according to the same model that we use in the lectures. We have a data set, right? So it is of the form d equal to xi comma yi, right? And I goes from 1 to say n, right? N data points. That is what we have. So I can now represent this as a feature matrix of size n cross n. Okay, and the label vector of size n, right? So this is, I hope, clear to all of you. Now each data point, as you all know, will lie in some m dimensional space, right? So okay, so that, I hope this is clear, right? So this is our setting for the data. Okay, so so what is the model in the case of logistic regression? What type of model is it? Any ideas, anyone?
An activation function.
Okay, we have an activation function, but is it a discriminative or is it a generative model?
It's discriminative.
Okay, so this is a discriminative model. So let's start from there. So this is a discriminative model. Therefore, what I'm trying to do, I'm trying to model p of y equal to 1 given x, right? So that is what I'm trying to model. And this is a probability, right? So I want to express this as a probability, and the function that I choose is called a sigmoid function, which is simply a linear. So I apply the sigmoid function on top of a linear combination of a weight vector and the feature vector, right? So x is the feature vector, w is the weight vector. They both have the same dimensions. I just do a linear combination, and then on top of that, I apply the sigmoid function, right? So let's very quickly go ahead and plot the sigmoid. So 1 by 1 plus e power minus x, right? So sigmoid will look something like this. Okay, so I think it got inverted. Okay, so this is between minus infinity to infinity, right? That's on the x-axis, and on the y-axis, it's between 0 and 1, right? So that is, this graph is something you'll have to remember. It's a very important, will come in very handy during the exam. Okay, so that's the sigmoid function, and that's your conditional probability. So what else do we have as far as the model is concerned? Any questions on this? Okay, so that is the model. We'll now go to the loss. I'll come to this decision boundary in a while, but let me quickly write down the loss for logistic regression. So can someone tell me the expression for the loss? Anyone?
It is minus of y,
Okay.
that is the actual level,
Okay.
and log of the predicted level.
Okay. So let me call that.
Y hat.
Yeah, that is y hat. So let's just write it down completely. Okay, that is okay. And then
Class 1 minus the predicted level
okay,
into log 1 minus.
okay, okay.
Sorry, this is yeah.
You are right. Yeah. So this is
And there will be
also a minus, right?
yes.
Okay. So this loss is in terms of what? What is this loss a function of?
This is the function of the weight vector.
Okay, it's a function of the weight vector, and this is for one data point. So I need to sum this across all data points. So I just let my index run from 1 to n. I just need to make this modification here, right? So this is yi, this is w transpose xi, this is 1 minus yi, and this is 1 minus w transpose xi. Okay, so that is your loss. This is called the binary cross entropy loss. Okay, so this is the same as what is this? What is the from where does this actually come? Binary cross entropy loss.
Maximum likelihood.
Yeah, so you try to maximize the likelihood,
Yes.
and then in the process you end up with the negative log likelihood. So probably that part I didn't explain. So let's go over that very quickly because MLE is kind of important, right? So no, not MLT, MLE, right? So this is what we have, right? This is the probability of seeing label 1 given x, right? So typically what you have a data set and you want to maximize the likelihood, right? And that is how, so what weight vector should I choose so that I maximize my likelihood? I can frame it that way. So how do I do that? I do it this way. See, for data point xi, this is the probability of seeing label 1, right? So this is the probability of, for data point xi, this is the probability of getting a 1. Okay, and if the label were to be yi, then this is that probability. If the label were to be 0, right, then I need to make this 1 minus yi, right? So is this expression clear? So this I'll just do this for all n examples, and since it's the likelihood, I'll call this L of W, right? Is this expression does this make sense?
Yes, sir.
Okay, right. So in case someone is confused, just look at it this way. If yi equal to 1, this term will vanish, right? This will become 1. So this is nothing but the probability of observing this particular data point, right? Xi comma y. If yi equal to 0, then this term will vanish. It will become 1. So you'll have probability of seeing a 0, right? So that is what this is. Now what you can do is you can take the log of this. So log of L of W. So this will become a summation, right? So this whole thing will become, the product will become a summation. So I will go from 1 to n, and you will have yi log of, just copy this, yi log of sigma w transpose xi plus 1 minus yi, right, log of this whole thing. Okay, so now this is the log likelihood, right? I want to maximize the log likelihood, or alternatively I can minimize the negative log likelihood, right? So this expression that we have here is called the negative log likelihood. Okay, and this is also called the binary cross entropy, right? So this is what we have. If you notice, let me just delete this part. This is what we ended up with, right? So this is the derivation for the binary cross entropy loss. Okay, so I hope there are no questions here. If there are, please stop me. So you can now differentiate the whole thing and set it to 0.
Sir, one question here.
Yeah.
The above one equation was already the binary cross entropy loss, right? The L1.
This one?
Not this one. The L loss binary. You told like that is also binary cross entropy loss, the loss function, which you have written initially for the loss.
This is what I wrote
Yeah,
initially.
the above one.
Yeah, this is what I wrote initially. So I just showed you how to get
Okay.
from maximum likelihood to the binary cross entropy. This is how you do it.
Okay, so what is that small LW function is being called? From where after that you have taken L. Yeah, this one.
Yeah. So this is called the maximum likelihood, right? So see, maximum likelihood is what? If I am given a data set, right? Given a data set T, how likely is it that this set of this data set is generated from this distribution?
Okay.
Okay, so if you remember, I think you did it in stats too. So if you're given a data set D of say n samples, each one of these samples is assume that it's being drawn from some probability distribution given by this P of y equal to 1. This actually what? This is a Bernoulli distribution, right? This is a Bernoulli distribution
Yeah.
with W transpose X as the parameter. Sorry, not W transpose X. Sigma of W transpose X as the parameter. Okay, so assume that all these data points are coming from this Bernoulli. I mean, not data points. I hope you understand what I'm saying, right? We are only modeling P of y given X. So assume that these observed labels are coming from this Bernoulli. Then for what value of the parameter W is there a maximum chance of observing this data set? That is what the likelihood means.
Okay.
Okay. So we try to, so our idea is to maximize the likelihood, right? So that's what we want to do, L of W, which is the same as maximizing the log of likelihood, which is the same as minimizing negative log likelihood.
How can it be same? I mean,
See, you want to maximize L of W. I'm saying that that's the same as maximizing log of L of W, right? Which is the same as minimizing minus log L of W, right? So if you want to maximize the function,
yes.
you minimize the negative of.
Yeah.
Okay, which is what.
Clear.
Yeah, this is also called binary cross entropy, right? So I hope until this point, all of you are on the same page. Okay, now we have to optimize this. How do you optimize this? It's an unconstrained optimization problem, right? So no constraints are there. So we can just take the gradient and set it to 0. I'm not going to do that part of the math, right? So that is not needed actually. It's good to know, but so this is the gradient of the loss with respect to W. So what will be the dimension of this? What type of an object will this be in the first place?
Will be a vector.
This will be a vector, right? So what will be how many dimensions will it have?
Same as the weight.
Same as the weight, right? So it will be same as the weight. So it will be like m dimensional vector. So how do you find I mean, yeah, that part I told we are not doing, but it's good to memorize the expression for the gradient. And I think it's one of the easiest expressions to memorize if you know what the terms mean, right? So I'll just show you a way to never forget the gradient expression, not just for logistic regression, but for several of these linear models. So the idea is simple. First, what you write down is the predicted value. Okay, the predicted value is what? Sigma of W transpose X, right? For a single example, I'm doing it, right? So let's do this for a single example. So for a single example, the predicted value is sigma of W transpose X. What is the actual label?
Y.
This is y, right? So so this is what? This is a probability, right? You should never forget this. This is something between 0 and 1. It gives you the probability of seeing 1 given x. So the closer it is to 1, the better is my model, right? So what does this term represent? Sigma of W transpose X minus Y. What physically, what does it, I mean, intuitively, what does it represent?
Predicted
It's a
label minus
probability.
actual label, the actual loss.
Yeah, the predicted label minus the actual, what you're
Actual
expecting.
label.
Yeah.
Mhm.
So what would it, what quantity is it? If you want to think about this as some quantity.
How distant is it from y?
Correct. So if it is smaller, then it's good for us. So if it is bigger, it's bad for us. So is there a name for this that I can? Error, right? So yeah. So this is some kind of an error, right? So the larger this quantity is in magnitude, the bigger is your error. So I treat this like some kind of an error, right? And this is not the total expression for the gradient. You also multiply it with that data point, right? So this is the gradient for a single example. Okay, so if I want to write it down in a simpler manner, it's nothing but error times the weight, error times the data point. Actually, it's a very powerful expression, because what this is saying is that when you're doing gradient descent for logistic regression, your gradient is made up of two parts. The first part is the error in prediction at that stage on a data point x, and the second part is the data point itself, right? So if you are like at the beginning of the training process, then you expect your error to be high, right? So your gradient matters at the beginning. Whereas once you are several epochs into the training, your error will be low, right? I mean, assuming that the data is like really like properly separable using a linear line, then your error will be small, and therefore your gradient will also be small. Okay, so this is a powerful expression. Just remember this as error times the data point for a single example. For a matrix, for a data matrix, right? For a feature matrix or data matrix X, what will happen? Let's write that down. Again, it's very similar. This will be so. Okay, so this is something I want you all to know. So if you have the data matrix X, what can you say about the rows of X? Capital X. What are the rows of capital X?
Features.
Number
The
of
features.
samples.
Okay, is it number of samples, or are they the
Features.
okay? Each row corresponds to one data point, right? So please remember this. X is n by m, right? So each what is this? This is something else I wanted into, right? Each row corresponds to one feature vector, or alternatively, each row is one data point, right? So the rows are the data points, right? And that is something you'll have to always keep in mind. Now, for if I call the data points x1, x2 till xn, this simply becomes I equal to 1 to n xi sigma of W transpose xi yi. Okay, it's just a summation of the data point times the error for the data point. That's the expression for the gradient.
So can we express in a vectorized form like X transpose E?
Yeah, that's what I'm coming to, right? So now you can, what you can do is the rows of the data matrix X are the vectors, right? So I just call this X transpose sigma of xw minus y. Okay, so this is the expression for the gradient vectorized form.
So when we learned the normal linear regression, it was X transpose, then there was no sigma, X omega xw minus y. because now there is a function sigma, we are just doing that prediction. Otherwise, nothing has really changed.
Yeah, exactly. Yeah. Otherwise, nothing changes. So for least square classification, same expression for without the sigma, as you said. For linear regression also, it's the same expression again without the sigma. Of course, y will be a real number there.
Yeah. So sigma is an identity function for regression. That's how we have to think.
Yeah. So sigma is there something that maps your linear combination between 0 and 1. So that is the only change, right? So this is, I think, quite easy to remember. If you remember this one formula, I would say if you remember this formula, it's enough. You can derive everything else from there. But yeah.
So I think for OPE, the second formula, because everything will be coding in vectorized form, it makes sense to kind of prepare for quiz and OPE together.
Yeah, agreed. Yeah. So there, this one is like more.
Yeah.
Okay, so that is the optimization part. Of course, now you just, all that you need to do is start with some, say, weight vector at time step 0, and then at time step t plus 1, whatever you had at time step t minus some learning rate times the gradient, right? So I'm just going to call that nabla of L of W. You keep doing this for set number of epochs and then you stop it, right? So that is how you learn the weights for logistic regression. Okay, any questions?
There is regularization for this also, right? Or no?
Yeah, there is. Yeah, you can add to the loss. This is the unregularized loss. You can always add one lambda times what? Norm W square, right? Let's say you are doing ridge. So I'm sorry, this tool sometimes is crazy. So
We can like regularize any convex function, right? Like it seems obvious.
yeah, you can always add this regularization, and you could of course transform x to some higher dimensional space, right? You could do, instead of xi, you could always have some phi of xi, right? That would make your algorithm even more powerful. So this is something you already know, right? So do a polynomial transformation of x using some phi of x, and then add some regularization. So that will give you quite a powerful model.
So in this case, the gradient we'll have to add the lambda by 2 times W.
Exactly. Yeah. So yeah, let's just make it lambda by 2.
Yeah.
So that it's consistent with, right? So this is lambda by 2. So you can just add the gradient will change, as you said, just plus lambda W will get added. All right. Any other questions in logistic regression?
So we add lambda W for the ridge and lambda plus absolute W for lasso, right?
Right. Yeah.
Yeah. Well, lasso we have never done actually. So
Lasso, I don't think you can differentiate. Right? Because
yeah, because it's because absolute value. So it's continuous, but not derivative is not possible.
Yeah. So that's why I don't think in MLT we haven't done it.
Yeah.
Right.
Is this L1 regularization or L2 regularization?
This is L2.
Okay.
L2 ridge.
Okay.
Right. So yeah, one final point before we close this for logistic regression. How does inference happen? So inference in logistic regression, I hope you all remember this. So this is you want to predict a y hat, right? So just give me this. Yeah. So this will be 1 or 0. When will this be 1?
When the predicted probability is greater than a threshold T.
Right. So the predicted probability is, in our case, sigma of W transpose X. Right. So that's probability of this data point being 1. Right. When that is greater than some threshold, we'll predict 1. Otherwise, we'll predict 0. Okay. So in the exam and in general, for when it comes to LR, our labels will always be 1 or 0. Right. Unless and otherwise specified, labels will be 1 or 0. One for the 1, we may also call it the positive class, and though it's not the right way, we may call 0 negative class, right? But yeah, so this is the inference in the case of logistic regression.
Sir, do we form a boundary line, like a decision boundary in case of logistic regression?
Yeah. So now, if you want to infer, how do you infer the decision boundary for LR? You look at it this way, right? So when do you? So the question is, when do you classify a point as 1, and when do you classify it as 0, right? So whenever the threshold is greater than 0, sorry, and elaborate. So whenever the probability is greater than the threshold, you call all those points 1, right? This is equivalent to, I'll just take the case of 0.5 threshold, it's easier. So remember that when is this greater than 0.5 for the sigmoid function?
It's a 1.
Greater than 0.
Right. So when
0,
this,
sorry. Yeah.
when this input is greater than 0, right? When the input to the sigmoid function is greater than 0, it's 0.5. It's greater than 0.5. And the input is negative, it's less than 0.5, right? So the set of data points that will be classified as 1 belong to this half plane W transpose X greater than 0, right? And likewise, the other half plane will be W transpose X less than 0. So your decision boundary in the case of logistic regression ends up being W transpose X equal to 0, right? So it's a linear decision boundary. So at the end of the day, logistic regression is also a linear model in some sense. Okay, so
and so one more thing, the points that are further from the decision boundary, that will have the higher probability, right?
Yes, yeah.
So I think there are a few practice questions where instead of just saying W transpose X equal to 0, we express it as a function of T also.
Right, yeah.
Right. If your threshold is not 0.5, let's assume it's T. Can we have a generic expression where we have that ln of 1 by T minus 1? So that will be useful.
Yeah, true. That is there in the quiz. So last year's quiz, we had that question.
Yeah.
So maybe you can all refer to that. I won't do that now because that can be a good exercise. Okay. So I hope there are no other questions. If there are any, please stop me now. Otherwise, I'll go to knife base. Okay, so the data is pretty much the same. So let me just copy the whole thing there. Okay, so we'll be dealing with the same data representation. Yeah, when it comes to model, as we know, this is a generative model, right? So that's the first point. So you try to model P of X comma Y, the joint probability. So when it comes to modeling the joint probability, this is what we do, right? So P of X comma Y is what we have, and we split it as follows: P of Y into P of X given Y, right? So few technical terms here. So the first expression P of Y, this is called the prior, and this is the likelihood, but I like to call it the class conditional density, right? So this is essentially something like a density function, right? And it's conditioned on a particular class, so it's called the class conditional density, right? P of X given Y. So your task is to model this whole thing, right? This is where the learning is going to happen. And why is it called naive base? Can someone tell me why it is naive?
Because it makes a very naive assumption that every feature is independent of others.
Okay, it makes a naive assumption.
It's actually a very strong assumption.
Right, it's a strong assumption. And what is that assumption?
That independent, conditional independence.
Yeah, class conditional densities are independent for all features.
Features are conditionally independent.
Okay, so features are conditionally independent. Okay. So it's a kind of tough word to write for me. Okay, given the class, right? So class conditional independence or features are conditionally independent given the class. So so what that means is that I can now, for each feature xj, I can model it separately, right? And I can model each feature xj separately, and this will be the density corresponding to that particular feature. Okay, and then so once this is done, the nice thing is that p of x comma y, I can write it down as p of y into, so what will this be, assuming that there are m features? How do I express this p of x given y?
It will be a product of all the features.
Right, it will be a product here. So let's p of xj, assuming xj is the jth feature given y, right? So this product will go from
1 to m.
1 to m. Okay, so this is what we have, and yeah, so this is the naive assumption. So what else do we have? And yeah, now, so the whole question now is, how do we model p of xj given y, right? So how do we model this? So what does it depend on? Like typically, what does it depend on?
Sir, it should be p of y given xj, na?
No, right? That is inference. P of y given x is when you are trying to find out what class has data points.
During the training, this will be correct, and during the prediction, that will be correct.
Okay. Yeah, we are in the model building phase.
Okay, okay, sir. Okay, sir. Okay.
Okay, how do we model this? Yeah, so it depends on what type of features we have, right? So we have, depending on the type of features, we have different types of densities. So it could be either Bernoulli, or in our course we have Bernoulli, categorical, multinomial, and Gaussian, right? Gaussian. So if xj is real, then it's Gaussian, and if xj is categorical, we can use a categorical one. If xj is binary, we use Bernoulli, right? So that is how we model it. So we'll just do the Bernoulli case. Okay, so p of xj given y equal to c, right? So we are now coming up with the model for feature j and class c. Okay, so j and c, that's what we have. So I'm going to express this as a Bernoulli distribution, because xj assume that it's binary, so it's a Bernoulli distribution parameterized by something called wjc, right? Wjc is nothing but, in the machine learning sense, we can view it as a weight, right? But in the probabilistic sense, this is the parameter of a distribution. Okay, so once I view this way, I can now go ahead, and there's no loss per se in naive Bayes. It's more of parameter estimation, right? So in naive Bayes, it's more of parameter estimation. And as you know, for estimating parameters, one good thing is the maximum likelihood. Once again, it comes to a rescue. So I'll just write down this expression for seeing one data point x comma y, right? So for seeing one data point x comma y, this is for okay, so can someone help me here? What are we trying to maximize?
The likelihood function.
Okay, so the likelihood function, right? So let's throw away the priors for now. Let's only look at the P of x given y part, right? So the notation is a pain. Okay, so this is, I think it has thrown a lot of you off. It also threw me off when I first looked at it. Can be a pain. So how do we? So do you want me to do the whole derivation for Bernoulli naive Bayes, or it's enough if we just look at the final estimates for weights? Which do you think is better? Any ideas? I mean, any preferences that you have?
So I think the final.
Yeah, final would be.
It is better, right? Okay.
In interest of the time, it will finally be better.
Okay, yeah. So we do a lot of things. We do MLE basically. We try to maximize the likelihood, and that will also be another optimization problem. Okay, so we'll try to maximize, take the gradients, set it to 0, and finally what we end up with is again for this whole WJC business, right? So feature J class C. So I'll first write the denominator because that's easier, and then we can take it from there. So you just sum. So sum over what? It's the sum over n examples. Okay, so sum over n examples. This is the indicator function. So you're going to look at all those examples that belong to class C. Okay, so get hold of all those training examples that belong to class C. Okay, and among those, you again have a sum I equal to 1 to n over the n examples. So you note that you are still looking at only those examples that belong to class C. So there is no change in that. So this should go here. But what are you going to add? In the numerator, what do you add?
Features, x.
Okay, so you add the features, but what feature are you going to add?
Those that belong to class.
Okay, so those that belong to this class, right? But that is taken care of by this indicator term. So what?
The jth feature.
The jth feature, right? So please excuse me for the notation, but I'm going to express it this way, right? So it's confusing to some of you. What I'm talking about is you have a feature matrix which is n cross m, right? So let me put it this way. So this is x1, right? First training example. This is x2, second training example, and so on, right? So let me write this as xi. This is the ith training example, and this is xn. There are n training examples. I'm calling xij as the xij is what? The jth feature
in the ith column, ith row.
In the ith row. Ith row is nothing but in the ith sample, right? So okay, that's what I'm calling as xij. So okay, so essentially what we are doing, if you look at it from this computational perspective, you are looking at all those rows which correspond to this class, and for all those rows you add the jth column alone and then divide it by the number of rows. So did you get the computational perspective of what's happening here? Did everyone get this part? What I just said?
So can you please repeat?
Okay, so see there are n samples or data points and m features, right? N samples and m features. Always remember that your data matrix or feature matrix is of size n cross m, right? So this is something you should never forget. It's always of size n cross m. So each row corresponds to one sample. So there are n samples, so n rows. Now the columns are what features, right? So the jth element in a row is going to be the jth feature of the ith sample. Okay, so all that I'm saying is that if you want to get hold of the weight corresponding to class C and feature J, you look at all those rows which belong to class C. See, each row belongs to some class, right? In the training data set, each row has some label associated with it. So you look at all those rows that belong to class C, okay, and find the number of such rows. So if it is still confusing, I'll call this NC, right? NC is the number of data points that belong to class C. And in the numerator, you have sum of all the features. So sum of the jth feature for all these points.
So essentially, it's finding number of whatever is the average value of jth feature in the class C, and then that is used in weight, and then finally for the parameter for our binomial, it's a linear combination of all those averages of all the features for that class.
Yeah. So the one saving point here is that Xij will take what values? So for Bernoulli, so we are discussing what? We are discussing Bernoulli base, right? So what values does
We'll take binary values.
We'll take binary values, right? So the numerator is actually those examples where the jth feature is 1, because whenever it's 0, this numerator will become 0, right? That part. So I can just express this as njc, meaning for how many samples is the jth feature in class C1. Look at those samples divided by the total number of samples in class C. Is this clear?
So can you say that this is the probability of appearing the jth feature in the class C?
This is the probability of, see how many times is the jth feature 1 and how many times is it 1 in class C. That's what we are essentially computing. Okay, so just let me just doing all this, I'm a bit worried. So let me go to the slides and make sure that we are not doing something wrong. So what is the formula given in the slides? Week 6. Okay, so we have the slides here. Okay, where is Bernoulli distribution? Okay, so there is like too many indices here. So see, this is essentially what we are saying. So it's the same thing, right? So I equal to 1 to n, yi equal to c. Instead of yr, I am saying yr is c, right? So look at all those examples of class C, and you are summing up the jth feature for that. Okay, anyway. So is this clear to everyone, or are there some confusions still?
The confusion is like you're saying it will consider only the positive values of
No,
YID.
I am not saying that. We can infer that, right? Because the Xij is either 0 or 1. So when xij is 0, that will not contribute to this sum, right? So what I'm saying is you will finally end up with this what I call njc is nothing but
Why xij will be 0 or 1? Because the feature can be any value, right?
no, right? So we are discussing Bernoulli name base. So you use Bernoulli name base only if your feature is binary, right? Not if your feature is say some real number. We'll not do Bernoulli name base. We'll be modeling it as Gaussian.
I thought this was more related to the label rather than feature. The Bernoulli.
No. This is no. The label actually is irrelevant, right? I mean, it could be anything. Label binary or even multi-class, right? So doesn't matter. What matters is how are we modeling p of xj given y, feature given label. So the what matters is the nature of the feature.
Okay.
Okay, so can someone tell me what njc is in the notation that we have here?
So number of times the feature j is equal to 1 for class C.
Exactly, right? So number of times feature j is 1 for class C, right? And what would nc mean?
Number of observations in class C.
Right, so if you know this, then yeah, that is all you need to know about. I mean, I won't say that is all, but this complex formula is essentially that is all there is to this formula.
So maybe we should solve a problem like, we have a binary, x1, x2, like 0, 0, 0, 1, 1, 0, 0, 1, 1. And then we have the counts. That should be it.
Right? Yeah, exactly. Yeah. So in the interest of time, I wouldn't do it. I may not be able to do it now, but for those who didn't get it, please go back and revisit this particular.
So can we also interpret this as the probability of given class C? What is the probability of getting J?
Given class C, what is the probability of
getting J?
What is the probability of seeing 1 in feature J?
In J, yeah.
Yeah, something like that. Yeah, you can.
Okay.
Sir, so this WJC is giving us only one column of the weight vector, right?
WJC is giving you one cell of the weight matrix actually. So I'll just draw the weight matrix here. So sorry, this is what. So maybe that may make it clear. So this is weight matrix. Okay, the weight matrix W has how many? What is the dimensions? And can someone tell me what the dimension will be of the weight matrix?
M cross C.
Okay, assuming there are k classes, it will be m cross k. Okay, so what your weight matrix is giving you is let me just add. It's giving you W. So sorry, what your expression here is giving you is one element in the weight matrix. Basically the jth row of W and cth column of W. That is what this is giving you. So you should do this for k into m such values.
K into m.
Yeah, because you have m features, right? So for so how do you do this? You for each class you have to model your feature given class, right? So always remember what we are trying to do. We are trying to model feature given class. So if there are k classes, then we'll have to model this for m features, right? So we'll end up having mk parameters for the whole Bernoulli name base. At least this part, p of x given y part, we need to model mk or estimate mk parameters. Okay, any questions?
Can you show the weight matrix?
Yeah.
Okay, clear.
Okay, so yeah.
when we do the multiplication, like W transpose X, that thing. So how will we do that?
No. See here, there is no W transpose X, right? That is only for like linear, though the perceptron, SVM, those models, right? Here it's not. The W is okay. The W is, that's why I said it's more of a parameter than a weight. Okay, so we call it W because we want to be consistent. We want some consistency in the notation.
I understood, sir. So, like in case of Bernoulli, we had this like in stats 2 we learned this parameter P. Here we are using parameter W.
Exactly. Yeah. WJC, right? W is a matrix, but for each Bernoulli is WJC, BR of WJC.
And so Bernoulli will be calculated like for how the Bernoulli will be calculated.
Okay, see, this is what we are actually, okay, I didn't mention this, but this is what we are doing, right? We are trying to learn WJC, right? So once you learn this, now assume that you have estimated the parameters. So now you need to inference, right? So inference will come to this. Yeah. So inference, how do? You do this as follows. You want to find P of y given x. Okay, so what's the probability that this belongs to class C given x? Okay, so this is nothing but P of y equal to C into P of x given y equal to C divided by P of x. So this P of x is common for all classes. So I'm just going to ignore that and I'll replace this with a proportionality. Okay, so that's what I'm going to do. These are priors, right? Priors, you can, again, you estimate priors in a very simple manner. So I'll just quickly write that down here. Estimation of priors is very simple. So what you do typically is, how do you estimate the prior? So P of y equal to C, you just say is the number of times, number of examples that belong to class C divided by total number of examples, right? NC by N.
Yes, sir.
So assume that you already have that.
So let's say I have been given a single data point. Now I want to predict the class which it belongs to. So can you like go through the process? What will happen?
Yeah, so that's what we are doing, right? So that's the inference part. So assume that you are given a data point X, you have to predict the class. So if there are like, say, 3 classes, right? So your C value could be either 1, 2, or 3. So for each value of C, you have to compute P of y given X and see which of these is maximum.
Okay. So in the prior that we are calculating, so prior will be from the training data set.
Yeah, prior and also your W's, everything will be estimated from the training data set.
W's will be from training data set. Priors will be also from the training data set.
Okay. Yeah.
So P of x given y equal to C, this will follow the Bernoulli distribution.
Yeah, so that let's expand on that. So that will be what? So this will, here you need to do 2 things. This you need to first break it down into your product of, so this is X is a feature vector, right? So you are using this naive assumption here and saying that this is a product of m values. Okay, you're doing this first of all. And the next step is you do this. So P of xj given y equal to C, this is where the Bernoulli will come, right? I'll replace this by WJC power
it will be at the, I think that sign will get omitted. It will be like WJC to the power number of 1 into W1 minus W.
Yeah, so it's so if xj is 1, this is just WJC, right? It's the probability of seeing a 1. That is what WJC means.
Yes.
Right, so it's either this or you don't know what exactly xj is, right? So I also need to make sure that this has the other term also. So Numerator will be 1 minus xj.
Yes, sir. Yes, sir. Understood.
Okay, so is everyone okay with this?
Yes, sir. Perfectly fine, sir.
Okay, so this is if xj is 1, this is wjc. The probability of seeing 1, if it is 0, then it's 1 minus w. Okay, right? So yeah, that is how we do inference in base. So priors, now this is for Bernoulli. You can do this for, maybe I'll just write it down for the Gaussian also. So for the Gaussian, what happens is you have a mu JC and also a sigma square JC, right? So you have these two. And now how do you estimate the mu? Is the mean of the Gaussian, right? So very similar formula. This formula is the same for all the cases. So you again look at only those data points which belong to class C, right? And that's all, right? I mean, there is no change in the formula actually. Only thing is that xij here will be a real number. Is that fine?
So there it has to be
Yes,
centralized, like xij minus xi bar square.
For the sigma square, right? Yeah.
Yeah.
So for the sigma square, yeah, we have to do the sigma jc square is we have to centralize it, as you said, it's mu jc, right? And you have a square. Is this right?
Yeah.
Okay, so this is the parameter estimation again done using MLE for the Gaussian case, right? So here you will have how many parameters will you have? There are m features and k classes.
Two parameters for each. 2 multiplied by mk.
Yeah, 2 multiplied by mk, right? So m for each feature, you will model it as a Gaussian with mean mu jc and variance sigma square jc, and there are m such features, and for k classes it is 2 times mk. Okay, so the nice thing about this, yeah.
So, sir, the mu JC will be matrix of m cross k.
Yeah, again that it will again be a matrix of size m cross k.
And this sigma square, that also will be m cross k.
Yeah. Let's just make sure, because these are all like crazy formula. So just make sure that we are not making any mistake. 1 by nr, number of examples in class YR, and then you are adding the jth feature. Okay, what we have used xij because we are using this notation. Okay, so that's the same thing.
That superscript is a turn off. I think this is better.
Yeah, agreed. That is like total confusion.
And sir, in like in the formula, it is given that we have to use covariance that matrix form. So not here, sir. In the latter part. In the like sigma to the power -1, there was a formula for Gaussian, no?
Yeah,
that is for multivariate.
Yeah, so
multivariate Gaussian.
Okay, so you can view this as a multivariate Gaussian also, but if you want to do that, then your covariance matrix will be diagonal. So these will be the diagonal entries of your covariance matrix, and off diagonal entries will be 0.
Yeah. So we can express this in vectorized, like xij minus mu j transpose times.
Right. Yeah.
In vectorized form.
Yeah, we could do that also. So it's good to know that I won't say it's, yeah, it will always come in handy. So please make a note of that also.
So just a quick question.
Yeah.
In naive Bayes, there is no concept of overfitting or underfitting. Is it because it's generative?
It's not because it's generative. It's because it's not a very powerful model in some sense. So naive Bayes, first of all, the assumption is very naive, and second thing is typically it's used as a kind of a baseline classifier in most settings, right? So you baseline, the moment you say baseline, you understand that it's like, okay, you just want to try out something so that is better than a random classifier, right? So typically it doesn't have enough capacity to overfit, right? Overfitting
Right.
comes in when your model is like so powerful that there is a chance of overfitting, right? So in naive Bayes, you really don't give a chance for that to happen because the assumptions you make are very strong, right? One is the naive assumption, the other one is, these are also strong assumptions, right? When you assume that your features are Gaussian,
The distribution.
it's also a very restrictive assumption.
Karthik, as part of zero counting, we do this Laplace smoothing and all that, right? Where we add some numerator and denominator constant. So actually is considered for overfitting and underfitting, right? Meaning too big a C will be overfitting and too less a C will be underfitting and all that. Is that understanding right?
I am actually not very sure about that. I think it's there in the slides somewhere. In the slides.
It is.
Yeah, I am not very sure of that because
since we are talking about it, it just cropped up in my mind. So
yeah,
even in naive Bayes, we have this overfitting and underfitting concept when we do the smoothing, right? As part of zero counting. That's where my doubt actually.
Yeah. So see this. I would say. I mean, I also this question was, someone else also asked this question. I think in discourse. So I would say that take the smoothing as something that is done to fix the zero count issue, right? When you are given a test sample and the count for that is 0, then you need a way to fix it. You do smoothing, right? Whether it really helps in reducing overfitting is something that I am not very confident of, right? So this I will get back to you, but for now, please don't think about it that way, right? I know this there in the slides, but yeah, that would be my answer for now.
Sure. Yeah. Thanks.
Okay. So any other questions in naive Bayes? Not, we can move on to. Okay, we'll move on to Canaan's. Canaan is like.
Sir, here what kind of questions can come from this concept? Because whatever the slides and whatever the Tendulkar sir has taught, right? There is not a single numerical example has been given. So I generally confuse when I solve PA and GA when it comes from particular concept. So if you can, it would be great if you can give one example of that, so that we can brush up the concept with the example.
Okay, so I will refer you to this. The couple of assignment questions are there, if I'm not wrong. Can you go and take a look at that? I won't be solving it now, unfortunately, but there is.
There are numerical questions.
See, there are few questions that you can. There's one numerical here, right? 7, 8, 9. You please go through 7, 8, 9. It's not real numerical, but it's kind of conceptual, so that will help you to some extent. And okay, graded assignment.
So this kind of questions can come from naive Bayes.
Yeah. Okay, so shall we move on? Canaan.
Yes, sir.
Okay, so Canaan, there is, nothing great about. It's a very common, one of the early algorithms, right? So K nearest neighbors. When you're given a test point, you have to just let's say this is the test point. I just make it uncolored, right? And so what you do is, given a test point, you look at k nearest neighbors to it, and if it's a classification algorithm, you do a voting, you do some kind of voting, right? So you look at how many of those k neighbors are how many of them belong to a particular class, right? And if say majority of them belong to class 1, or say the red class, then you predict this point as belonging to the red class, right? And for a regressor, what you do is you look at the k nearest neighbors and you take the average of their labels, right? So that is how a KNN regressor would work. So typically the issues when it comes to KNN are one is the choice of distance metric, right? The other is choice of k, right? So distance metric, typically you have Euclidean or Manhattan, right? So I mean, so basically L2 and L1, right? In some sense, this is L2 and this is L1. Okay, so the choice of k, how do you do it? You can go for some kind of cross validation, right? You have a validation set where you try out different values of k, say k equal to 1, 3, 5, so on, right? And you measure the misclassification rate or the accuracy, right? So how many points are getting classified incorrectly? So there will be some trade-off, right? So at some point of time, you will see that misclassification rate keeps going down and down, and say probably for k equal to 5, it hits the lowest value, and then from then on it starts increasing. So what you would say is, okay, the choice of k for this data set is 5, right? So that is how you'll choose k. You could do something similar for the distance metric, but when it comes to higher dimensional problems, metric is really it may work, it may not work, right? So the whole curse of dimensionality comes in there, right? In higher dimensional spaces, we don't know how distances work really, right? So that is one big problem when it comes to KN for high dimensional problems. So one more thing you need to know is, so what are the issues? Can someone tell me what problems, disadvantages, I'll call them that. What are the other disadvantages of using KNN?
Computation for the training data.
Yeah, so both computation and memory, right? So memory, because you have to store the whole training examples, the whole set of training data, right? So there's no model per se. So other point to note is that there is no model you are building in the case of KNN. You just have a training data set with you, which is loaded into memory, and at test time you just query each point in the training data set and see and select the top k neighbors, and then you do the prediction, right? So there is no model as such in KNNs, so you can't throw away the training data set. So if you remember logistic regression or linear regression, once you get hold of the weight vector, you can essentially throw away the data set, training data set, and just using the value of w you can do your predictions. Something like that cannot be done with the k in the case of KNN. You need to have the training data set with you at all times. Okay, any questions? I think this is like one of the very simple algorithms. So
sir, just again, a low k will result in underfitting, is it, or overfitting?
Yeah, so this is, see, to be very honest, I am also very confused about this part, right? So
a low k makes a lot of islands, is what I realize as an image.
Right. So a low k is going to optimize for very fine structure in the data.
So it will be basically focusing on local. So it will be overfitting for low k. So you'll get a little bit more smooth surface when k becomes slightly larger. Otherwise, for small k, you'll see a lot of rough edges, a lot of overfitting in a local region.
Yeah, I'm not sure if I would call that overfitting. I agree that it'll capture local structure and it'll try to learn that local structure, but would that Is that equivalent to overfitting? I'm not sure.
Well, the decision boundaries will be the decision boundaries will be a lot of nonlinear, and there will not be a lot of smoothness. So in other words, you will try to learn and memorize a lot to the training data, and then your generalization error will be higher when you go and try to test it on out of training data sets.
But actually, here the decision boundary doesn't matter. It's because every test data we are going to do see which label it falls in by doing that.
So other disadvantage is a non-parametric. So hence the power and is also lower compared to other parametric form of models.
Yeah. So because it's non-parametric, it scales with the data set size, right? So that is the whole computation and memory angle. So it as your training data set scales. So if 100 training examples becomes 1000, then the time it takes to predict a new test point, it's also going to scale with that, right? So yeah, you are right. So yeah, that is with regard to KNN. Any more?
One question like, what is the difference between L1 and L2 in this scenario? Because means L1 is also sufficient, right?
Yeah, they're just two choices that you have, right? It's just like you don't know which choice which K to choose. Likewise, you don't know which metric is going to be better. This is kind of empirical, right? So you have to empirical. What is the spelling?
I think both of them will give the same result, right?
No,
it may not, right? It depends on your data set.
So we have seen examples where by choosing the distance metric, your inference point could be either class. So it's sensitive to the distance metric you have chosen.
Yeah. So this is important. The point is we don't know there is no one distance metric which is like universally good for all kinds of data sets, right?
No, for Manhattan and Euclidean, suppose I get a Manhattan distance of 3. So I'm just squaring that 3 to get 9, right? So
no, right?
How does it matter?
No, right? We are not just squaring. So this is, okay, see, this is Euclidean, right? So this is, Euclidean is what? If you are given, I'll just take two features, right? So this is x comma y, right? So I'm calling Euclidean on two vectors x comma y. So this is x1 minus y1 square plus x2 minus y2 square, right? This is the Euclidean metric. Now the Manhattan is what is Manhattan? It's
the absolute difference.
Yeah, it is x1 minus y1 plus x2 minus y2, right? This is not the square of that, right? I'll call it, say, d2. This is d1.
Yeah, but effectively, like if I have to compare, right? So both of them will give the same result.
Not necessarily, right? So they won't give you the same result. So I would request you to go back and look at quiz 1, right? Quiz 2 of last term. In quiz 2 of last term, we have a question on Manhattan and Euclidean. It's a nice question. So that you go back and look at it, okay? So you will get your answer
Sure. Okay.
there. So okay, so in general, right, this can be extended to any other LP norm. I don't know if the formula is correct, but so you can essentially do something like this, right? Instead of doing a square, you can do
P.
Raise it to the power of p, right? So this is the LP norm in general. That is L1 in the case of L1. I think it is the mod comes up, right? So, but in the case of other LP norms, I'm not sure, but you can also look at these things.
Yeah, it will not be square root in this case. It will be like 1 by p, the power.
The power is 1 by p, is it? Oh, sorry. Okay. Yeah, it's better I don't write it down because I'm not too sure about the LP norm. So let us just search it.
We raise it to power p and take a root of p.
Pth root of that. Okay.
1 by p. Raised to the power 1 by p.
Okay, okay. So power p raised to 1 by. Okay, okay, got it. So this mod also is important apparently. Okay, anyway, right? So okay, so that is about K-nons. Any other questions in K-nons? Okay, so if not, we'll just move on to Softmax regression. See, Softmax regression is just the extension of logistic regression to multiple classes, right? So here it's useful if you write down the dimensions of certain things. So X, as you know, is n cross m, n samples, m features. So instead of a weight vector, you have a weight matrix. So can someone tell me what the size of the weight matrix is going to be?
N cross K.
Sorry, what cross K?
N cross K.
No, M cross K.
Okay, it is M cross K. Okay, so that is your weight matrix. Now the model is going to be what? Linear combination followed by softmax, right? So the model is going to be linear combination. What is the linear combination going to be?
XW.
XW is the linear combination. Okay, so yeah, oh right, yeah, we have the B follow here. I forgot. So dimensions of B will be what?
N cross 1.
M cross 1, right? I'll just write it as dimensional feature vector. So the label, okay, so instead of a label vector, you have a label matrix of size
N cross K.
N cross K, yeah.
Okay, so N cross K. So each row of this label matrix will have how many ones?
One hot encoding, right? So there'll be only one.
Yeah, each row of this matrix will have one. Okay, so please don't forget that. So XW plus B is the linear combination, and on top of your linear combination, you do a softmax. So you do the softmax row wise or across the rows or across the columns?
Across the rows. Across the rows, number of samples, right?
Right. So you do it along the rows. I mean, along the rows in the sense. Okay. So what is the dimension of XW plus B? Let's start from there. One step before you take the softmax. What will be its dimensions?
Sir, here, what is the softmax? I mean.
We'll come to that, right? I'll come to that. So before we go to softmax, see XW plus B dimensions.
N cross K. N cross K.
N cross. Sorry, this is N cross. Okay, N cross K. Now see, this is one slight catch. B is not. It's not for each feature. This is for each class, right? So this should be K dimensional. You don't have a bias. You have a bias for every class, right? You don't have a bias for every feature. There are K classes, so you have K bias values.
Yes.
Right. So this is everyone? Does everyone agree that this should be N cross K?
But B we will be having it for every rows, right?
B you will have for every
rows without any weight. That I mean, like the dummy feature kind of a thing. B, and we can absorb that B with the XW as well if we want to.
Correct. You could do that. So the
yes,
W.
So it will be for every rows, right? B N, it should be N. I am not sure though. Why K?
See, B stands for what? The see if W, let's look at it this way. If K is just 1, what will happen? If K is 1, what does it reduce to? Softmax regression. Sorry, K is not 1. K is equal to 2.
Logistic.
It kind of reduces to logistic regression, right? So,
Regression. Yes, sir.
so should it be for in logistic regression? If you okay, logistic regression, if you want to represent W transpose X as say something, so it's not equal to, I'll just add a comma and write it separately as W transpose X plus B, right? So will you add B for M features or will you add B just once?
So we will add B for each what to say, data points for each row, right?
Correct. Here also we are going to add it for each row, but how many such B's will you add? You will add only one B for one class, right?
One B for one feature, like one row.
No. So I get that you are right. So you will add one B for one row. You will add it for n rows, but you will add only one B, right, for that one class. Now we have K classes. So you will have a feature, you'll have a vector of K B's, right? I mean, or B of size K, which you will add across all the rows.
So what will be the dimension of XW?
XW is n cross K.
So, and what will be the dimension of B is K? B,
yeah.
dimension of B is K. So,
yeah. So
n cross K plus K, how will it get added?
It will be added row wise. So this is the whole NumPy broadcasting thing. So see, XW is what? I'm saying XW is n cross K, right? And I'm saying that B is K. So I'm going to add this K dimensional vector to each row. So I'm still adding it for each row. For each data point, I'm adding B. But that B is of size K. Right? Okay, so look at it this way. Tell me if this is clear. So let's take. So this is 2 cross 3, right? This is XW. I'm saying that this is XW. Just randomly filling up values. And then I'm saying that by B is say 7, 8, 9. So when I add XW plus B, this is how it's going to look, is what I'm saying. You will add 7, 8, 9 to each row of XW.
Yeah, broadcasting.
Right. So this is NumPy broadcasting, but I hope this is not confusing any longer, or is it still confusing?
So this B is what 7, 8, 9 is for each class.
Yeah. So there are 2 examples here and 3 classes. So there is, see, the whole idea is there is a bias. Okay. So you are now, okay, how will you try to bring this? Let's quickly see if we can somehow bring this as a part of the.
A smart way to do that would be if I add K-1 column with one hot encoding to my design matrix, then we don't need the B term outside, just like, it will be embedded within the X. That will be a better way to do it.
Yeah, that's what I'm also thinking. Okay, so that alone it needs a slightly longer discussion. Now it's already 9:40. So this part is okay, right, for all of you? It's one bias term for each class.
Yes,
okay.
sir.
Okay, so
the class is in Y, right? So you should probably put a Y also. It looks like it's for every feature in this.
Right. So Yeah.
And sir, one question here, like how the B with this dimension 1 cross 3 will get added with XW, because for that it should be of same shape, right? For the addition.
Yeah, but so see here we are abusing notation. This is a slight abuse of notation. Okay. So what I'm saying is that it's kind of understood what is happening here. Okay,
No, I'm considering the example which you have given down, XW and B. Yeah. So can you please tell how it will get added?
so this 789 will get added to 123, right? So this will become 8 plus. If you add XW plus B.
8, 10, 12, right?
Yeah. So I don't know the exact computation, but so this will be what 8. Yeah, 10, 12, and then 11. Whatever 8 plus 5, whatever that is.
Okay, so it will be added to the both the rows.
Both the rows, yeah. So every training example it has to be added, right? This bias.
Okay. Okay, sir. I'm good.
Okay, so moving on.
So, sir, in logistic regression also we are getting B of so 2. The dimension of B will be 2.
No. In logistic regression it will be 1 because so we are not separating it into 2 classes, right? We have like we have only one weight vector. So when I asked you to think about what will happen when k is equal to 2, I just wanted to kind of tie it back to logistic regression, but in logistic regression this is not the way we exactly model it, right? Because there we don't use softmax, it's the sigmoid, right? So don't bring that again because that might end up confusing you.
Okay.
Right, so it's like keep them separate. I think that is better. Okay, so now the whole point now is
just one clarification.
Yeah.
If you just roll up a bit. So,
yeah.
So this will be K labels, right?
K yeah, K labels. Yeah, you have K classes. So
here K will not be the class label, it will be just K label.
Which one are you talking about?
The B, N, and K. So this K classes should be K labels, right?
K labels, yeah. So
we have multiple labels. That's it.
Yeah,
multiple
we have
outputs.
we have some. Correct, yeah. So something like this, we could encode it this way.
Right. Because classes can be within the labels. So you can have multi-classes within the multi-output.
So typically, if there are K classes, then we'll have to do K minus 1, not because the residual probability will be 1 minus sigma of all the other probabilities, right? So
okay. So there are different ways of doing it. So I am doing it in so in the slides I see that you have there's a different way of doing it, but you could do it this way also, right?
But in this case, the matrix will not be a full rank, so we have to be aware of that because of the dependency of probabilities.
Yeah, but that's fine, right? We are not really taking an inverse anywhere, right? It's all like just a transpose. So even if it's not full rank, I think.
Okay, got it. Yeah.
My doubt got clear, sir, because this will not be actually K labels, this is K classes only, because we have done one hot, so it actually shows as multiple out, right?
So this is a single label multi-class problem, right? That's what
single label, yeah, it's a multi-class problem, but only one label.
Yeah, so it's like we are trying to classify. There is a fruit, and we are going to classify apple, orange, or banana, like 3 labels, right? Yeah, but only one fruit. Fruit is one label.
Exactly. Yeah. Okay, so the softmax now is going to happen across the columns, right? So if you think about it, the whole thing is n cross k, right? So softmax of xw plus b for each data point should return a vector of k probability, right? So it should be a k-dimensional vector for each data point. Okay, so if you actually expand this this will be what? This will be a again n cross k matrix, right? So the let me call this, what do we call this? Let's call this matrix y hat. Okay, so if you call this y hat, then for the ith data point and jth class, right, this is going to be of this form, right? E power
I.
Yeah, so do we want to write, so this xw plus b, maybe, I don't know, I think in the collab it's called z, if I'm not wrong. So let me also call this z. Okay, so the ijth element of this matrix, Z matrix, and then you sum it across the J features, sorry, M features, right? Or sorry, here K classes. You sum it across the K classes. Z, same row. Maybe I'll use a different variable if this is confusing. Let's call this C, right, for class. This is the softmax. Now let me just create some space and have all this on the page. Now, do you all agree with this? See, Z is what? The linear combination, right? So Z is XW plus B. For n data points and K classes, this is the matrix you get of linear combinations. Now you want to convert those linear combinations to probabilities, right? For each row, you want a probability. So how do you do that? You take an element in that row, call it Zij, right? So you raise that, you exponentiate it, right? Like e power Zij, and you divide it by e power Zic for all the elements in that row.
So to assign it to the final class, we have to take the max of those probabilities across rows and then assign the class.
Yeah, yeah. So the final class assignment is you will do an argmax of this value. Okay, but you will do that over C, right? So this is the maximum will be over the classes. So that class for which in that particular row you have the maximum value, that is your predicted class. Now, is this clear to you all what is happening in the softmax?
So, sir, if there are J features, so let's say I have 3 features and 4 rows. So now in that case, my Y, the softmax will be for each cell, we can say.
Okay, so see the feature at this stage, the feature is like already consumed by your model, right? So what your Z matrix is just a linear combination. See, the features have already been linearly combined and only that output you have with you. So this is like for n samples, for the 4 samples that you have and the 3 classes, whatever values you have, that is what Z is actually. 4 cross 3, right?
So, n cross K basically. In this case, K is, yeah.
So that XW, when you do XW, your features get consumed in that. See, X is what? N cross M. W is M cross K. So that linear combination kind of already takes care of this feature conversion, right? Feature weight manipulation. So it will return one number for every.
So, sir, what will this Yij hat will give me?
So what Yij hat represents is how likely is it that point I belongs to class J. So Yij is Yij, to be very precise, Yij, sorry, is going to give you probability of sample or data point I belonging to class J.
Sir, assuming if there are three classes, let's say the fruit classification problem, banana, apple, and orange. So every row will have three probabilities, and the addition of those three probabilities will be one. So essentially, whatever is the highest, that will be my class that I'll assign, right? So that is true for all rows.
That is true for all rows.
Yeah.
Sir, class there you mean to say class J or class C?
Class J here. I mean that is here. It's you could use J here also. So it's the same, right? It's just an index. This is just the index over which you are going. So look for that element in the row which has the maximum value. That is the maximum probability. And that is your predicted class.
Okay, sir.
Okay, so is everyone clear? Softmax regression, what's happening?
Yes, sir.
Okay, so this is the model. See, very quickly I will we will so optimization we are not going to do because it's like very fear-inducing, especially before exam. So we just look at the gradient. Gradient is again very simple, right? So if you look at the gradient of the loss. Now, interesting thing is the gradient is a matrix, right? So it's since your weight is a matrix, your gradient of the loss is also going to be a matrix, and it has this nice expression of right. Recall that this X transpose was there for logistic regression also, and there it was sigma of XW. Here it's softmax of XW plus B, right? Instead of, if you want to express it in that way, so that it's now do you see the connection between logistic regression and softmax regression? So if W became a vector, then and softmax is turned into sigmoid, this will be logistic regression. Instead of that, you have W being a matrix and Y being a matrix, one hot encoded matrix. So that is the only difference.
So here, what is the argmax J?
Argmax part is actually the inference, right? So see, you are having a bunch of probabilities in each row. Okay, so something like you have, for the first training example, P11 will be one probability, right? P12 will be one probability and P13 will be another probability. So say this is 0.2, 0.4 and 0.4, something like that. So what we are asking is look for that value in this row which has the maximum probability, right? And whatever column you are looking at, that particular column corresponds to the predicted class, right? So for example, if this is 0.1, this could be say 0.2, then this will be 0.7, right? So argmax is what it's saying is that look at these three values, check the maximum value, that is 0.7. 0.7 belongs to class 3. So you predict this particular data point as belonging to class 3.
Okay. So here the output will be 3, class 3.
Yeah, output will be 3. Predicted label will be 3.
Okay.
Okay, so I hope this is okay. Can we move on finally to SVMs?
Yes, sir.
Okay, so
it looks
SVM,
like it will be midnight today.
Yeah. So SVM will probably try to, since we have done quite a lot, so data remains the same. So recall that the model is something like this, right? So you try to fit the best possible hyperplane best in some sense, right? So it looks something like this, right? So this is where we want to go towards, right? So see, this we did it quite extensively in the week 8 session, so I'm not going to go over too much of content. The main part in SVM is what you have to maximize the margin, right? So margin is basically the distance of the nearest point from the boundary, right? So what is the distance of the nearest point from the boundary? So there are several points in the data set. So you're going to look at that point. Let's say in this case it's the red point, right? And these two blue points, these are closest to the boundary, and you want to, in some sense, maximize the margin. So we want to maximize the margin. That's our goal, right? So first thing is we need to find the margin. So for that we need to know what is the distance of a point from the boundary, right? So let's go ahead and do that. So if this is the distance of, so the boundary is what? Boundary is given by what equation?
W transpose X plus B equal to 0.
Yeah, right. So boundary is given by W transpose X plus B equal to 0. So the distance of a point from a boundary is going to be this value, right? W transpose Xi plus B absolute value by the norm of W. So this is like distance of any point xi from the boundary W transpose X plus B equal to 0. Now the margin is nothing but the maximum of the dA, right? So that is the margin, and so this, assume that there is some point, say xj, for which this distance is maximum. So let's call that point xj, and just add it here. Xj is closest to the boundary, right? And therefore dj is the margin, right? So your margin comes down to an expression like this. Now if you recall, if W transpose X plus B equal to 0 is the boundary, then if I multiply both sides by k, nothing changes, right? This is still the decision boundary remains the same. So if I multiply both sides by some non-zero value k, my boundary is going to remain the same. This means that there is some control over the values of W and B. I have some control over the values of W and B. So what I'm going to do is I'm going to choose W and B in such a way that this is equal to 1 for the points which are closest to the boundary, right? So I'm going to set this to be 1. Moment I do that, my boundary becomes, sorry, my margin becomes 1 by norm W, right? So
actually 2 by, if you...
oh, right, yeah, I missed that. Yeah, so this is, yeah, so there is one more step here. So for a linearly separable case, we can rewrite this expression as yi into W transpose Xi plus B by norm W. We can get rid of the mod sign, because when it's linearly separable, you know that W transpose X plus B into Y is always positive, right? So that is something you must know, right? So yeah, you are right. So this is crucial. Okay, so this is the expression for the margin, 1 by norm W. In the slides, it's 2 by norm W. So, I mean, we are really not going to ask you what's the value of the margin and things like that. So you don't need to worry about that. But essentially, you end up with a minimization problem, or rather a maximization problem. It says maximize the margin Okay, but this is the same as minimizing the reciprocal of the margin, right? So that is minimizing norm W, but norm W is like I'll have square root of all these things, right? So it's not very good to work with. So I would rather minimize the square of norm W, and for mathematical convenience, I will add 1/2 here, right? So this is what I finally end up with. The objective function that I want to optimize in the case of SVMs is minimize squared norm of W by 2 subject to some constraints, right? So what are they? If you notice, every point on either side of the margin is on either side of this bounding plane, right? So these are called the bounding planes, right? So every point on either side of this bounding plane is away from it, right? So the closest points are these red and blue points, which lie on the bounding plane, but every other point is far away from the bounding plane. So that results in the following constraints: yi into w transpose xi plus b is greater than or equal to 1. So this is what is the optimization problem in the case of hard margin SVM. Okay, so is this clear? Is there any confusion in this hard margin formulation?
Yes.
Sir, just one question.
Yeah.
Sir, in case of the logistic regression, we from maximum to minimization, we just added the minus.
Yeah, right.
And here we inverted the that function. So is there any general rule how when we have to invert and when we have to add minus?
Okay, so good point. See there, the form was already kind of decent, right? It was, see, typically we go for minimization problems, right? That is one criterion. We always try to formulate it as a minimization problem. Especially in ML, we do that because in the logistic regression case, right? We had maximize the likelihood was the formulation, and then we said minimize the negative log likelihood. There, the negative log likelihood, I start treating that as a loss function, right? I can think about it as a loss function. Okay, so I want to minimize the loss. I somehow want to bring everything into that form. Here, the reason I do this reciprocal is slightly different. 1 by norm W is hard to work with, right? When it comes to differentiating this, optimizing it, right? It's hard to work with 1 by norm W. So norm W square by 2 is a smooth function, which is differentiable. It's a very well behaved function. So here there is a specific, the reason I do this kind of trick here is slightly different from why I did it for logistic regression. Okay, so does that answer your question?
Yes, sir, but I couldn't get the generalized rule.
Generalized rule, yeah, I'm not giving you that. I'm just telling you in these two cases why we did what we did.
Okay, sir.
Okay, so in general, right, if you want a general rule, I'm not very sure, right? You typically go for minimization problem, number one. Number two, you want to make sure that the functions that you're optimizing are well behaved or smooth, right? Continuously differentiable, all these things have good properties, basically.
I think we are looking for mathematical convenience here.
True, yeah. So smooth functions are good to differentiate. So, I mean, that is a part of why we are doing it here. Okay, so this is hard margin. I hope all of you are clear. This is hard margin.
So I have one query. Can you go back, up to the diagram? So here in the diagram, we have the red as well as like one red and two blue dots on the boundary. So is it necessary like both the classes will be on the boundary?
See, you must have at least one point belonging to either class on the bounding planes.
Perfect. That's fine. Yeah.
Right. So at least one. So it need not be like this. It could be like this. Okay, not like it could be like this also, but it can't be like something like this. right? Where only one point in one class belongs to the bounding.
So you need support vectors to estimate the hyperplane.
Yeah, you need support vectors, and the nice catch there is you need at least one support vector of either class to be in the mix.
Yeah.
So until we find that situation, there is a possibility that we will go far away, and there will be noise in between, right?
So the good news is that for hard margin case, you will always find this, right? You will always have, because it's linearly separable, you will always be able to find this scenario where.
Okay. The decision boundary will lie in the center. Okay, got it.
Yeah.
Okay.
Sir, in the diagram.
Yeah.
So suppose we have one support vector on either side.
Okay.
Then orientation of these lines can be means anywhere at any degree. Or
not at, see, the orientation will be such that the margin is maximized. The only thing that the orientation will depend on that line. Obviously, our goal is not to fix the orientation, right? Our goal is to maximize the margin. So whichever decision boundary maximizes the margin, your orientation will be decided by that.
Yeah, but we can change the orientation in this scenario also, right? Without affecting the logic.
Suppose, sir, if we have two vertical lines, then also
we can rotate it. Yeah.
No, it depends on the boundary, right? If I see the way I have drawn it, maybe is not the maximum margin, but whatever is the maximum margin, the boundary corresponding to that will have a certain orientation, right?
But for this scenario where we have just 2 points, we can rotate the decision boundary.
No. So if you have just 2 points, right, the decision boundary will lie on the perpendicular bisector. If you do some geometry, you will realize that the decision boundary will be the perpendicular bisector of the line joining the 2 points. Okay. Anything else you consider, right? It will fall short. So if I
cosine distance.
Got it.
Right?
Yeah, cosine distance should be maximum.
Yeah.
Yes. Thank you, sir. Thank you.
Yeah. So that is the hard margin case. Now the next is the soft margin. I mean, you can solve this, right? You have to solve this. So you convert it into the dual, you do all that business, and then finally what happens is you end up with this expression for the weights, right? So the weight, after you solve the optimization problem, which we are skipping, has a nice expression like this, right? So this is alpha I ya x. Weight is essentially a linear combination of the n data points, but several of them are going to be 0, right? So only some alphas are going to be non-zero, and those alphas which are non-zero are called the support vectors. Okay, so in the diagram that we have here, you will have only 2 non-zero alphas. One alpha for this. Every data point will have one alpha, but only 2 of them will be non-zero. All others will be 0.
Sir, here I have a question. So when we are solving any, numerical question given to us in graded assignment, we are using this linear combination. But there we are writing something like alpha into S1 into S2, alpha dot S1 dot S2, something like that.
See, that question is actually not. Don't worry about that question. That's not like that. That question will not repeat in quizzes. We'll not give you like estimate. Inspection. Look at the diagram and by inspection method find the support vectors. That question, we have had some problem with it in last quiz, last term also. Okay. So that S1 dot product S2 business, right? Whatever is there in that we won't ask.
So it was in graded assignment also. So
yeah. That nature of questions will not have, because it's tough to estimate support vectors by looking at the diagram.
actually, sir, my query was not related to the which are the support vectors, but more like what we are doing there. Alpha 1 into S1 into S2. We are kind of multiplying two support vectors.
Okay. See, what we are doing there is essentially something like this. So, see, for a given data point X, right? W transpose X plus B, the sign of this will give you the prediction, right?
Yes, sir.
So I can now rewrite it because I have the knowledge of W being a sum of a linear combination of support vectors. I can now write it as Xi transpose X plus B, right? For any point X, this is how I can write W transpose X plus B.
Yes, sir. Yes, sir.
Okay,
Here,
yeah.
What is the first X and the second X? If you just can.
See, here Xi's are the training data points. X is the test point that I want to predict, whose label I want to predict.
So Xi is the training data point and X is the label that I want to predict.
X is the test. See, X is some test point that is given to me, whose label I don't know. The Xi from I equal to 1 to n are it's the training data set.
Training. Okay.
Okay, so typically this is what we have. So those alphas which are non-zero are your support vectors. So these Xi's are your, right? And so Xi's are the support vectors. Another important property for support vectors is that what will this expression be if Xi is a support vector?
Will be 1.
This will be 1, right? So in the hard margin case, all your support vectors lie on the bounding planes, right? So this will be W transpose Xi plus B equal to 1. This will be equal to -1. But if you multiply that by Yi, then you have this, right? Always equal to 1. For support vectors, right? Please make a note. For all the other vectors, it is greater than or equal to 1, right? Sorry, greater than. For anything which is not a support vector, it is greater than 1. For a support vector, it is equal to 1. Okay, so that is hard margin. So,
sir, can you explain those questions where we have to choose the suitable kernel?
Suitable kernel. See, I will give you a very general idea of what a kernel is, but I am not sure if we'll have time for. One thing I can assure you, we will give you what kernel to use, right? So we won't ask you to choose a suitable kernel. That is not going to happen.
Sir, one general doubt, sir. In the previous term quiz 2, there was a question on kernel where they were given where they have given two vectors and they have said to find the kernel tree, but there like what will be the degree to, like, kernel is we do the dot product and then we transform it into a higher dimension. So what will be the degree of that? They have not mentioned.
Yeah. So that's what I told. Right? So we will explicitly if a question related to kernels are appear in the exam, we will tell you, say if it is a polynomial kernel, what degree polynomial you should use. So the exact specification of the kernel will be given to you. So we won't ask you to choose the appropriate kernel, right? That we will not do.
Okay. So like there was the answer, the dot product was 51. So there was two options. One was 51 and one was the square of that. So by intuition, I chose the square. But can 51 be the answer? Like, can there be a kernel which is transforming it like in degree 1, basically keeping it in the same dimension only?
I am not sure. See, that question is ill-specified, as I said, right? It's not.
Okay. Okay.
You could see, you could choose any kernel, I believe, right? So depending on the kernel that you choose, your k of x comma x1 comma x2 will turn out to be different. So I really don't. To be honest, I don't understand that question that much. But if we are asking you a question on kernel, you will be given what kernel to use.
Okay, sir.
Okay, so for the soft margin case, I'll just modify this self. So your points are not linearly separable. So you could have something like this happening, right? So, right. So this is something like this could happen, right? And the moment something like this happens, you have, say, what is called a slack entering into the picture, right? So I just show it for one data point. See, ideally this red point should have been on this side of the boundary, but it is on this side of the boundary, right? Wrong side of the margin, as we say. So there is some slack psi associated with this point. Okay, so I am allowing some slack. So it's okay if this point is on the wrong side of the boundary, but I am allowing these points to be on the wrong side, but I am at the same time measuring by how much they are violating this margin, right? So if this point had been here, anywhere here, or on the bounding plane, the slack would have been 0, but it is on the wrong side. So I end up contributing some slack or allowing some slack. For each point I have the slack. So what I do is I still want to maximize my margin, but there also comes in some slack for each data point, right? So, and these two are, if you think about it, these two are like, they work in opposite directions, right? So if I want to maximize my margin, so if I want to move this way, then my slack is going to increase, right? See, all this point earlier did not have a slack at all, but because I want to maximize my margin, this point is now going to get some slack. If I still want to increase the margin, then this point will also get some slack, right? So what we see is that increasing the margin, which is the first term of the objective, works against reducing the slack. Okay, so to kind of mediate between these two, I have some parameter called C. Okay, so the C will kind of help me adjust between these two tendencies of maximizing the margin and minimizing the slack. Okay, I hope that is clear. Now, if the objective is clear, then there is one small modification that we need to do. Right now, since there is a slack, I don't need this to be strictly greater than or equal to 1. I need it to be greater than or equal to 1 minus the slack. Okay, is this okay?
Yes, sir.
Okay, so this is the typical soft margin case, and here the weight will come out to be again the same thing, but small difference is that support vectors are not just the points that belong to this bounding plane, right? You can also have these values as support vectors, those that are on the bounding planes and those that violate them, rather not and, those that are on the bounding planes or points that violate the margin are all going to be support vectors, right? So for example, in this case, you are going to have these two as support vectors. These two are also going to be support vectors. Is that clear? There are four vectors, four support vectors here for the soft margin case. Okay, any questions about the soft margin SVM?
So this is it because we add this penalty C sum of Ci that it becomes an unconstrained optimization problem? Because the way it is treated is it's treated like an unconstrained optimization problem, right?
Okay, so see, this is still constrained because you have these constraints. Now, what we can do is, yeah, okay, so I totally missed out that part. So we can come up with an unconstrained version of this problem. Unconstrained version of the soft margin case, which is, you have this, right? So what you do is, you can basically express this slack as, slack is always, okay, so there are several things I missed here. So this is not the only constraint. You also have, okay, remember that the slack is always non-negative, right? So if you have, slack is always measured from the plane that, the bounding plane that this should have been, that this should have belonged to, right? So this red point should have been beyond this bounding plane, but it is here. So this distance is what I call the slack. So it is always non-negative, right? It is either 0 or it is positive. So that is one more constraint. So
it's always greater than 0, right?
Greater than or equal to 0. It could also be 0.
Yeah, if it is on the bounding.
On the bounding plane, or if it is already correctly like on the right side of the margin. For these points, it's 0. This is also 0, but this is positive.
I think in the lecture slides they made a mistake because
they made a mistake. Yeah.
One from the bounding plane to between the bounding plane and the decision boundary, it was shown as slack being less than.
Yeah,
0.
that is wrong. Yeah, that is wrong. So that needs to be corrected actually. So it is always non-negative, right? So it is all either 0 or positive. Okay, so now I can now rewrite this whole problem as soft margin SVM as max of 0 times 1 minus right. See, yi into W transpose xi plus b is the distance from the bounding plane, right? So that is this distance. 1 minus that will be this remaining distance, right? So I hope you get it. So this distance will be negative. So let me just make it explicit. This distance will, I mean, this is a signed distance, right? So this will be what? This will be okay. So this is this distance, right? This will be negative. Do you all see that? Why this is negative? Because ya is actually +1, but this is okay. So this is negative. Now, now this distance is what?
1.
That is 1, right? So that is 1. So let me just add that here. So 1 minus this is nothing but this whole distance, because this is negative, right? Minus of minus. So this 1 minus this yi into W transpose xi plus b is the slack. Okay, so I can now write the slack as 1 minus yi into W, this whole thing. But for the other points, this will be negative, right? For those points which are correctly classified, for this W transpose xi plus b is greater than 1. So 1 minus this will be negative. So for all these points, the slack is 0. So that is how I come up with this max of 0 comma expression. So effectively what I have done, I have converted this constraint optimization problem, these two constraints, I have now added it as a term in my objective. Okay, so
and therefore it becomes unconstrained.
Therefore it becomes unconstrained, and then there is we saw one solution using SGD, right? So and yeah, so here few points. First is C is some kind of regularization constant, right? So regularization constant, if you remember, for it's actually 1 by c if you think about it, because see, in linear regression and logistic regression we had lambda into norm of w square, right? Whereas here, if you divide this by c, right? I mean, let's just, if you divide this expression by c, the maximum will not change, right? So 1 by c is some kind of a regularization constant, okay? And this term is what we call the hinge loss. Okay, so this is basically your some kind of misclassification loss. Okay, so if your points violate the margin, the more they violate the margin, the more the hinge loss, right? So for points that are on the right side of the margin, they do not contribute to the loss, but points that are on the wrong side of the margin, they contribute to the loss. So when I say wrong side, it doesn't necessarily mean this side, right? So it need not just mean this side, it could be even here. Here also there is a loss. Here, what is the slack? The slack is this much, right? There is this much slack here. So anything on the wrong side of the margin or the bounding plane, that itself is going to contribute to the loss.
But sir, in that case, the support vector will be changed now.
I mean, yeah. So here, this will also be a support vector if this is the case. You're saying the bounding plane will change. Is that what you're saying?
Yes, sir.
Yeah. See, this is just an example, right? I just moved it temporarily. Like, I mean, if you move
it cannot be, sir, within the bounding planes. The point cannot be, any point cannot be in the bounding plane.
No, right? It can be, right? So we are dealing with soft margin SVM.
Okay.
Right. So see, when the whole point of soft margin SVM is when your data points are not linearly separable, so you could even have there's no way you can find a bounding plane to separate this point, right? And I mean, like, you cannot draw a linear hyperplane to separate this perfectly. So there are going to be points even after you train the SVM which lie on the wrong side of the bounding plane, and they are also going to be your support vectors.
Okay.
So, sorry, in other words, when we have unseparable cases, we have two options. One is we tolerate slack variable and use a soft margin SVM, or if we do a kernel trick, go to a higher dimension and where it is linearly separable, then we don't need any of this slack business, right? We can separate, have a perfect hyperplane which is going to separate the plane in a linear way, right? So really,
it's not this or that, right? It's like this. We could do this and that. So what if even in that higher dimensional space, after using the kernel trick, what if the data points are still not separable, right?
Yeah. So in that case, you go to, like somebody was asking, instead of going from R3 to R6, you go to R9. So the whole idea is there is a dimension, if your original dimension is Rm, you go to some M plus K, whatever. If that K is sufficiently large, you will always find a linearly separable hyperplane. But again, that's
right. Yeah, that is kind of a bit, hard to imagine. But yeah, so it's usually in practice we have the soft margin SVM and then we apply the kernel trick on top of that, right? So we kind of do both. So now that we have brought up the kernel, very, very quickly we'll see what the kernel is. I think I didn't
do. I have one doubt, so if you can, before
starting
this, if you can go to the diagram above.
Yeah.
So this distance of 1 is from this bounding plane till the decision boundary, right?
Bounding plane till the point. Till the decision boundary. Yeah. So this.
Okay.
That is this one.
Okay. So if anything comes between this, we don't have a misclassification in 1 between.
Yeah. Anything between.
So this red. these two is not a miss. So this red point is not a misclassification.
This, yeah, when it comes to inference, this is not a misclassification. However, this will still contribute to the hinge loss. Okay, so that's a subtle point, right? So there are, see, what you are penalizing is not necessarily only the misclassification. You are penalizing, so this is what you are penalizing. Your margin violations, right? So this is made up of two parts. One is, this is very bad. This is correctly classified, but on the wrong side of the margin, still on the wrong side of the margin. This is bad, right? So this is bad. This is very bad. So the violation is much more here. But what is bad about this is that this is misclassified. This also counts towards your hinge loss. But the good news is that this is correctly classified.
Okay, right.
So if you're estimating the classification accuracy of a model, I think, yeah, that's where the difference will be.
Exactly. Yeah, visible. Right. Yeah. Right. Okay, so this is a subtle point, but it's an interesting point in SVMs that we are not. So what we are penalizing is not just the misclassifications, but even if you are correctly classifying something, you want it to be away from the margin, right? So that's the bottom line of SVM. You don't want points close to
what I recall from the hinge loss is anything less than 1, the graph, the hinge loss graph, was a misclassification. Anything less than 1 was a misclassification, right? And anything more than 1 was 0. That's how the graph.
Yeah, the graph looks something like this, right? L shaped. I mean, where the L is a bit slanting. So anything less than 1 will contribute to the hinge loss, right? It will have a non-zero slack.
Okay.
But it need not necessarily be misclassified because.
Okay.
Yeah, misclassification is just the sign of. So classification is sign of W transpose X plus B, right? So the bounding planes do not come into the picture for while predicting the class. It is only the decision boundary which counts.
Right, got it, sir. Right.
Okay, so see the whole kernel business is you actually must know why the kernel is useful. For that we need to go to the dual and all that, but we don't have time for that. But if you recall, where is this? Yeah, so recall, if you try to formulate the dual expression in terms of Lagrange multiplier, right? I don't know how many of you remember, but we got some kind of an expression like this. Sigma alpha I over all. So these are the Lagrange multipliers. Minus, we had a double summation yi yj xi transpose xj, right? And we had alpha I alpha j. Okay, so this is like again overall training examples I equal to 1 to n. This is like a nested loop, right? Nested for loop. So we try to maximize this, right? This is the dual formulation. So now where do kernels enter is here, right? If you want to solve this optimization problem, the only thing you need is the dot product between xi and xj. You don't actually need individual values of xi and xj. Only thing you need is dot product. Same thing when it comes to prediction. If you want to predict, you essentially do what? You take the sign of W transpose X plus B, where X is some test data point. So, sorry. So this is what you do, right? So you take sign of this expression. Here again, notice what matters is the dot product between xi and x. Okay, so the idea of a kernel is basically this. So given two vectors x and y, can I come up with some expression which is equivalent to a dot product in some higher dimensional space. This is the whole idea of a kernel. Okay, is this the reason why we are using kernel clear?
Yes, sir.
We use X and Y, but I mean, in practical sense, it will be Xi and X, the new data point, right? That's what.
Yeah, so it will be Xi and X, let's say Xi and Xj. While trying to optimize, it would be just Xi transpose Xj wherever. So
right.
In the test scenario, it will be Xi comma X, as you said. So okay.
Right.
Okay, so the nice thing is, so there are these advantages, or why we have a kernel. The first motivation is, the only thing that matters is dot products between feature vectors. First point, right? Second point is there a way to get the dot product in some transform space, right? In some, without explicitly computing the transformation. Okay, so there are 2 points to the kernel. First is our realization that the only thing that matters is dot products between vectors. The second is the kernel is giving you a way to compute the dot product in some higher dimensional space without actually computing that transformation, right? So this is what is happening. So for example, if you take the polynomial kernel, it will be something like this, right? So Xi transpose Xj, say whole power 2, right? This is a degree 2 polynomial kernel. This actually corresponds to some 6-dimensional space. I'm not exactly sure, but if you actually try to compute phi of x and phi of xi and phi of xj, you will notice that you are actually operating in some 6-dimensional or higher dimensional space, right? And you are finding the dot product in that transform space. This is what it amounts to, but you're doing all of this implicitly, right? You are not explicitly computing phi of x. You don't have to. That's what a kernel does for you. Okay, is that okay? The reason we are using kernels?
Yes, sir. So one doubt I have, sir.
Yeah.
If you can just go up where the dual is presented as a dot product.
Yeah.
So this, so if you can just briefly explain the second summation with j is equal to 1 to n.
Yeah.
I am clear.
See, what is happening is that this is nothing but pairwise dot products, right? You have, say, 10 data points. Now, what you want to compute is xi transpose xj for every pair. Say, first data point with second, first with third, first with first. Likewise, you will do it for, it's like a nested for loop, right? For I equal to 1 to n, for j equal to 1 to n, xi dot xj is what you are computing.
Okay.
So
when we say that we are putting a Lagrangian in the SVM, so we do it data point wise.
We do it for the end data. We don't. So yeah, it turns out that we do it data point wise, but actually what we are doing is we are doing it constraint wise. So if you look at, let me bring this dual below, because see, there are n data points. So subject to, for 1 less than or equal to I less than or equal to n, you have n inequality constraints. So this is where the Lagrangian comes in, right? For n constraint, you have n Lagrangian, and it so happens that there are n data points, n constraints. Okay, this is actually the dual formation for hard module. So if you want, for completeness sake, you can just add the constraints. So subject to alpha i's are non-negative, so that is one constraint. and the other constraint is sigma alpha I yi will be 0, right? So this you don't need to remember, but it's good to know.
So then I'm still confused. Where does this J come from?
See, J is not the feature, right? If that is the confusion, J is not the feature. J is, see, it's just an index. So I could have even used, say, K, right? And made it
maybe I2, I1 and I2.
It's all possible pair of dot product between the rows. That's how we should think. If there are 10 rows, the number of product will be 10 times 10, 100.
Yeah, you are 100 10 by 10 matrix where you are computing pairwise dot products between all the vectors.
Okay. Okay. Got it.
It's like a row operation, dot product on the rows. We are not really worried about number of features which are in columns.
Right. Yeah. Okay. So I think that is, so we have this is one kind of kernel, and this is the polynomial kernel of, so you can just replace this with P, you will get any other kernel. So you have also the other radial basis function, right? So e power x minus something, right? Whatever, norm of x minus x bar square, right? So some crazy formula. So these are two types of kernels, but the more essential thing is to understand why we are using kernel in the first place, because it gives you implicit dot products in transform spaces. All right, so I think that's all I had.
So can you share this, or you'll have to go through it?
So unfortunately, I am not in a position to share it.
Okay.
Right, because yeah, so for certain reasons, I am not in a position to share it, but I hope you can come back to it if needed.
Right, sir. We'll do that.
Sir, I have one question. Like, can you share, like, if you have previous question or any mock with the solution, if you can share?
Previous year's question papers are, I think there are like quite a few threads discussing them. So what you can do is, see, we are ourselves running out of questions. So if I share the solution also, then it's like I will be helping you for Sunday's exam. So you can ask on discourse, and either one of us or one of your peers.
Previous year's papers are there already, right?
Yeah, already there. So in fact,
where is it?
There is no solution.
Sorry, sir.
I'll give you the link.
Yeah, solutions are not there, but some questions also have solutions discussed on discourse.
Okay.
The question on computing the width on the linear separable case from weight vector.
Yeah. See, that's actually, like, honestly speaking, that's not the right. I mean,
that's the right question.
See, okay, so assuming that you have trained in SVM, assuming that you have obtained a solution, then 2 by norm W is the like 2 by norm W or 1 by norm W is the margin, is the width of the margin, right? 2 by norm W. If you want this whole distance, right? That is 2 over norm W. That is the.
Okay. Similarly, this spam question also, one more small doubt on the spam question is, when we are doing all these things, what is the probability of spam is unable to understand from them, while rest of the things are there.
Okay.
P of y given x equal to P of y into P of x given y and P of divided by P of x. This calculation we are able to do. All things are coming. One is that P of spam. That one I am able to get from.
P of spam is the prior, right? P of spam is just the prior. So total number of spam.
So it has to be assumed as 0.5 as given.
If it is a balanced data set, right? If there are like 50 spam messages and 50 ham messages, then it is 0.5. But if it is like 70 spam messages, then it will be like 0.3, 70, 30. So that you have to estimate. Prior estimation is like straightforward, right?
Here it is given as assume that the prior probability is equal to 0.5 for each class.
Then you have to take it as 0.5.
It is a 50-50 balance. Okay.
Yeah.
So in that P of spam, we can put this 0.5 and find it. Then also one number which is coming 0.00006 kind of thing. But after that, how do I know that whether it is threshold meeting or not meeting? That threshold kind of thing.
So there is no threshold, right? It's only a question of P of
the final. They say one example is there. P of spam given want more money.
Correct.
So in that case, coming 0.5 into 0.03 into 0.02 into 0.02 into 0.0, something with 6 zeros and 6 is coming. So yeah.
You have to compare these two probabilities. So this might be very small. So say if this turns out to be bigger than this second one, then you can classify it as spam. So the posterior is what matters, right? Which posterior is bigger?
Sorry, please. P of y to the spam given x
is greater than if this is
both
greater
of this
than
we have to calculate.
Yeah, you have to calculate both.
Oh, I have calculated only one.
Yeah. So that is the typical recipe, right? For all classes, you have to compute the posterior. All right. So is that all?
Both and then.
Yeah, you have to compute both and see which of the two is greater. Okay then. So anything else? If not, we'll.
No, sir. But thank you very much for this session.
Thanks a lot, sir. Like understood everything. Like every time I attend your lectures, so it's complete new learning for me. And thanks a lot.
Yeah, thanks all of you for joining. So all the best for Sunday.
Thank you very much, sir, for this session.
Thank you very much.
Yeah, thank you. Thanks everyone. Yeah.
Thank you.